It is my pleasure to introduce Jesse Thrift. He is on loan to us from the U.S. Coast Guard. He's been here since fall of 2023, and they really want him back. So we're in a bit of a hurry to push him through this program here. He's originally from Upper Harborough, but lives in Higginsville now with his criminally adorable 3-month-old son here. He's got a lot of things on his plate. Jesse attended the University of Maryland, got a BA in 2012 in English literature, which is not a STEM field you all recognize. Then he joined the Coast Guard, initially performing, correct me when I'm wrong, naval engineering duties aboard ships in Jonesport, Maine and Homer, Alaska. Then as a deck officer aboard ships in Fort Huron, Michigan. All very cold places.
Yeah.
Next up, he went to Cleveland, where he started managing Drydock maintenance procedures for Great Lakes Coast Guard ships. And this is where one of his prime responsibilities was trying to understand and mitigate or remediate possible environmental problems from bottom paint application and removal. And it became obvious, the epiphany, that he probably ought to learn what that actually means, so he decided to get a master's degree. And he's come here to study and understand the possible implications of release of these materials into the environment, in the landscape. And we quickly decided this should be a methods project rather than a real field project. So I'm not going to go into a lot of detail, I'll let him describe that. But after taking some chemistry and biology to get caught up, he's been with us 20 months. He's cranking through his project very well. He actually won the AG&R Cornerstone Research Poster last fall, so a little award there. And he is going to leave here shortly to be the branch chief for the Small Boat Depot Maintenance for Surface Logistics Center for the U.S. Coast Guard in the Navy Yard in Baltimore. So we'll still be local. Thank you.
Thank you, Dr. Yankos, for the introduction. I also owe a lot of thank yous at large to everyone from this department. I've been helped by many of you throughout this process, but specifically thank you to Dr. Mullinax and to Dr. Soon of UMCS, who's not here, for serving as members of my committee. And also thanks to Ms. Sabina Malik and Ms. Cassandra Gabalis and Dr. Ray Weil, who have all helped me in various capacities, including editing, providing access to their XRF instrument, and teaching me how to use it and how to understand the results it gives me. I would also like to thank, I gotta click. There we go. I'd also like to thank the Coast Guard Office of Naval Engineering for funding my attendance here, and Coast Guard Surface Forces Logistics Center, Coast Guard Yard, and Great Lakes Shipyard of Cleveland, Ohio, all of whom assisted me with collecting samples, and their staff were in various capacities super helpful teaching me about paint and the state of the industry. And again, another thanks to Melissa and Calvin. I am only here because of them. Briefly, I'm going to talk about what I'm going to cover today. I will be discussing ship hull coating maintenance and why it matters, the maintenance of those coatings in dry docks and how they could affect the environment, the use of XRF to identify traces of these coatings in the environment, and toxicity testing of contaminants of interest and those field collected sediment samples. You all are familiar with this PowerPoint slide. I've used it a couple of times. The short version is that we paint ships because they rust. We paint them with anti-fouling coatings because things want to live on them. We don't want things to live on them because it'll increase their CO2 emissions and make them cost more. So we're going to save money and we're going to save the environment. Huzzah. There are a few ways you can mitigate biofouling, including in-water hull cleaning and some different products. The main one I'm going to talk about is dry dock processes. Ships are dry docked every 3 to 5 years. They are dry docked more frequently, the worse their paint works. The first thing that happens when they're dry docked is they are pressure washed, as in that lower right-hand photo there. That can cause some release in the environment of paint and miscellaneous media, but it is primarily done to take off algae and light films on the hull so you can inspect the paint. Once you inspect the paint, you decide how much you're going to remove and repair. If you get up to 30%, you will probably do 100%. If you are below 30%, you'll probably do a spot repair. Regardless, you're going to do some abrasive blasting. That middle photo is showing what that process looks like in an open floating dry dock. They go in there with a compressed air system that blasts sand, not sand anymore because that's going to kill you, but different products that are very abrasive to remove paint and to prepare the steel substrate to receive new paint. And then finally, you will paint. Every step of that process can cause the release of stuff into the environment. They try to mitigate that. Depending on where you are, they will go to different lengths to mitigate. In the state of Maryland, we have very strong laws about what kind of containment you got to provide. Other states have similar laws. Seattle is notorious for it. Well, Washington State's notorious for it. And others have more loose regulations. That left-hand photo there shows Coast Guard Yard in Baltimore. That is a scaffolding that has been built around a ship. There is ventilation installed on it. There are grit separators in the drains to collect stuff. No waste is going to escape from that project. That right-hand side photo is the same floating dry dock from the last slide. There are tarps at either end where it's open, and there's tarps at the doors on the wing walls on either side. But it's open on the top, so dust can fly out that way. And as you can see from that photo, that tarp is broken. It was COVID. They couldn't get it fixed. They tried to patch it with a smaller tarp. That didn't work. It's the Great Lakes. It's windy. End result was that we lost a bunch of stuff into the lake. And that's kind of what inspired me on this project. There isn't a ton of research on what is the result of this mixture getting out, this abrasive media mixed with paint, where it goes, how it ends up, how toxic it is. So that's how I got started. And then I kind of went off on more of the methods side after that. Anti-fouling coatings, more generally, this is what we're looking at. There's a lot of detail I could go into. I have drilled down. I'm only going to talk about the parts of this graph that are relevant to what I'm doing. So I looked at a chemically active paint, specifically soluble matrix, which means that the binder that contains the biocidal pigment degrades and floats off into the water the same as the biocide does. There's two kinds of those, self-polishing copolymer and controlled depletion paints. Controlled depletion paints are less effective. They do not degrade. The binder doesn't degrade as well, so they need more biocides in them. They can have a couple of different chemically active ingredients. They aren't all toxic. Most of the common ones in use now are. Some of those are organic. Lots of these paints use organic compounds as booster biocides. And lots of the primaries are metallic or organometallic. There are 6 metals that are in common use or were in common use. We have tin, mercury, lead, copper, zinc, and silver. Tin, mercury, and lead are all either banned or no longer in use in the industry. Tin was famously banned back in the early 2000s. It was used in an organotin form called tributyl tin. It was having a lot of unintended consequences on the wildlife. So they banned that. They banned red lead, a specific type of lead that was used as a biocide before that. And I couldn't find anything when mercury was banned, but it's not used anymore. Lead was also frequently used in conjunction with other paints. Specifically, copper paints used to use a lot of lead. They don't use as much anymore. The other 3 that are still used, silver is uncommon. There are a few products that are approved with it. It serves as a booster biocide. Copper and zinc are very common. They're in all kinds of paints and all kinds of structures. It includes metal powder and particles. It includes oxides. And includes organometallic compounds. The most common is copper 1 oxide or cuprous oxide. And the most common zinc is typically zinc pyrithione, which is one of the organic molecules. It is worth noting that not all of these are biocidal. Specifically, I want to call out zinc oxide, which is often used for UV protection, and it's not officially toxic. It's in your mineral sunscreens that you're going to use because you're trying to save the reefs. And the particles for zinc are not typically used for their anti-fouling properties. They're used as anti-corrosives in areas of either high foot traffic, high abrasion, or like high cavitation from a propeller. The zinc serves as a sacrificial anode, so it rusts instead of the substrate beneath it. Try and get through this quick. I don't have much time, and I have a lot of material. So, can the copper biocides in anti-fouling paint be used to detect microplastic paint particles in the sediments near shipyards? Is my overarching question. My specific hypotheses are, will my XRF readings reproducibly forecast the toxicity of these sediments that are collected in the field based on their copper content? Second hypothesis being, when I go out there and look in the field, we find increased copper concentrations near shipyards in these industrialized rivers? And my third and final piece being, will the copper component of my field spike sediment dilution series correlate with my field collected sediments based on their copper contents? To cover this, to assess this, to figure this out, what I did was perform toxicity tests using a variety of lab-generated materials, copper compounds, paints, abrasive blast media, and field-collected sediments finally. And then I used the XRF to assess the dilution series I made to see how much copper they actually had. I used it to design a blast media dilution series because I didn't know how much copper was present in that blast media that I collected in the field. I used it to analyze my field sediments to see how much copper was present in those. And I finally used it as kind of an aside. I was concerned I was losing some copper in some of my test replicates. So I used it to assess the overlying water from my toxicity tests to see if there was a copper change in those. The copper compounds we used were cuprous oxide, copper 1, and copper sulfate, copper 2. We chose these two because they are both very well studied and used as biocidal agents. On land, copper sulfate is used in farming, especially orchards and vineyards, and it is used residentially, I keep trying to say recreationally, as a root killer. It's also used as a fish feed, funnily enough. Copper 1 oxide is used primarily for anti-fouling paints as a biocidal component, but it also has a lot of other uses, including just as a pigment for coloration. The point of having these two is that A, they're both pretty well studied, and B, they have different charges, and cuprous oxide is insoluble and copper sulfate is soluble. So we kind of got our opposite ends of the spectrum there. I also want to take this time to mention that there are not any regulatory sediment quality guidelines in this country for copper. Some other countries do have them. A couple of examples there. Canada has 197 for freshwater and 108 parts per million for saltwater. Australia has 270 parts per million for saltwater, and those are kind of the thresholds where you'll start to expect to see a toxic effect. And then I have Wisconsin up there because we did start to develop some guidelines that weren't made official. Some of the states still have them or have similar ones. And in Wisconsin, they use a threshold effect concentration of 32 and a probable effect concentration of 150. I'd also like to mention at this point that there are a lot of other factors that do go into copper toxicity or metals toxicity in general. That graph at the bottom is from one of the papers I found talking about Australia's establishment of guidelines for this, where they studied the toxic thresholds compared to percent silt in the sediments and percent organic carbon in the sediments they were looking at. The paint sections. So I used 3 paints for this study. They were all Sherwin-Williams products donated by their Elkridge store. They're all Coast Guard approved in the sense that we will use them on our ships. We do not have a regulatory role in the approval of biocidal paints. That's all covered under the EPA, covered by the EPA under FIFRA, like they're a pesticide. And the 2 primary ones were controlled depletion paints, so they're higher content biocide and they deplete less effectively. One using cuprous oxide with cupric oxide, so that's copper 2, as a booster, and one using zinc pyrothone as the primary biocide and an organic compound called trilopyryl as a booster. I keep using that word, so briefly, a booster biocide is present in a smaller quantity, is intended to kill things the primary biocide misses, especially like biofilms that'll cover the skin of the ship so that you can't access the primary biocide. And the third paint was an anti-corrosive epoxy, which is essentially just a very thick inert coating to protect it from the salt water. As part of a complete coating system, it goes on first and the anti-fouling goes on top. We also collected field samples. The first one of them being last on this list, it is my used paint sample from Coast Guard cutter Laguerre, which was docked in October 24 at the Coast Guard Yard. I got there the day after they docked. They were pressure washing the stern. I went up to the bow and I scraped paint off with the paint scraper, took it back here to the lab. I know that paint is an ablative copper anti-fouling paint. I do not know specifically which brand. There are several that are approved for our use. Some contain organic boosters, some contain only metals, some contain metal particles. So I have a certain level of knowledge about that, but not 100% accuracy. I also collected used abrasive blast media, so media that had been used to take paint off of a ship, so therefore was mostly inert sand-like coal slag mixed with copper paints. First, in November 23, I collected from Coast Guard cutter Sequoia's midlife maintenance availability. It's in there. The ship is there. You can see the silver in the top corner. They've taken all the paint off. Everything on the deck there is abrasive media mixed with paint. It is enclosed. It has not been contaminated by anything aside from what came off of the ship, and no wind or environmental action has lost things to the environment. Then in Cleveland in July of 24, I went up there for other sampling purposes, and I went to the yard and they said, hey, we finished working on a boat 2-3 weeks ago. It was over there. We did painting. We did abrasive work. You can go take some samples. So I did. You can see there that red stuff, that is all paint overspray. It's not dirt. They painted the boat red, and everything that was left on the deck turned red. The black stuff there that you see, that is abrasive media, or it is, they have an engineered ground surface, they call it. It's just gravel with illusions of grandeur. So that's a mix of stuff. It's also been a yard since at least 1950. So there's years of contamination there, and because it's in the open, they could have also lost stuff to the environment. This stuff comes down very fine and light, so I would predict that, not predict, I know this has less copper. I think it's because the wind caught it and blew it away. And that's there where I got the paint from. So far as spiking my sediments goes, I had my first series with the copper compounds. We got dry weights for our clean Y River reference sediment that we were spiking these materials into. And we calculated how much of the compound we would need to add to get a dilution series that maxed out at 5,000 parts per million. And then we diluted it down to 2,000, 1,500, and 250 on a by weight basis. Once we had added the copper compounds to that, we rolled it on a rolling mill on the right-hand side for 5 to 7 days, took it off, and then we prepared our dilutions by mixing clean Y River sediment with the correct ratio of the spiked sediment to get our little range there. For the paints, we use the same process, but we don't know the same way that we know how much copper is in the compound. We don't know how much copper is in the paint. We went off the packaging. The packaging says 49% by weight. The safety data sheet says, oh, it's between 20 and 45%. So there's different regulatory standards there. We don't know which is accurate, but we went with the 49% number. You may remember back when I had the slide up about the paints I selected. I just painted the paints onto thin plastic silicone little craft sheets and on paint trays, let them dry, and then I broke them off of there, and that's how I got my material. I had to go through a couple of iterations. My first few looked like this. They're very thick. They're a real pain to work with, and they didn't cure very well. Their texture isn't quite right. So I went back and I painted it more thinly, and I got something that was a lot easier to pulverize using the little bead blaster lysine machine that's there on the left. And then I was able to spike those into my sediments. My anti-corrosive epoxy was painted thicker, and it is designed to be very hard and tough and hard to break up. We used a coffee mill to grind that up. It is important to note that the masses involved here were very different because obviously there's a lot of copper in my compounds and very little comparatively in the paint. So we had about 70 micrograms of, milligrams of copper 1, 160 of copper 2, and then we had 8.6 grams of the paint. For my non-copper paints, we didn't have a target concentration of any given metal. We were trying to simulate what we would see in the environment if we had been maintaining a hull and we lost a lot of paint. So we used the same mass of my non-copper anti-fouling paint and my epoxy paint as we used mass of my copper paint that we had selected based on the copper content. And the final spike series was my abrasive media, which we spiked in based on our XRF readings, which I'll go into a little bit more in depth later, but we added a boatload, because there's very little copper in that overall, 200 grams of that to 800 grams of clean sediment. I'm going to take an aside to talk about my XRF, Dr. Weil's XRF. For those of you who aren't aware of how this instrument works, it has an X-ray emitter and an X-ray detector. It bombards a sample with the X-rays, which then excite electrons in the inner orbitals of the atom, causing them to bounce out. This forces electrons in higher orbitals to come down. When they come down, they lose energy, which is released as more X-rays. Those X-rays are emitted at a known wavelength or a known energy, and the instrument can then count how many signals at each wavelength or energy it receives, and it can use that to tell you how much of the given element is present. It's, I wouldn't say a weakness, but a point that is relevant is that it needs to be calibrated to the specific matrix you are looking at, whether that is soils or plants or the lead-based paint painted on your 1940s era house. If it's not calibrated, it will not give you accurate numbers, but you can use it to give you those counts of those elements that it sees, and you can then say some things about the relevant amounts between two samples that are the same matrix. It also does not tell you what compounds are present or what their charge is, but it is very commonly used in metallurgy and in soils and environmental assessments and lead-based paint assessments. It has a benefit in that it is very quick to use. You can get a sample result in 60 seconds and you look at it right there on the screen, you know how much it thinks is there. And it is quick to train people to use it. So it has a very low cost per use. The instruments themselves are expensive, but once you train someone, they can do 60 an hour, you know? So that's a nice advantage. This is a specific instrument that Dr. Weil has. It's a Bruker Tracer 5. It can detect everything between sodium and uranium, just with air normally. And if you purge it with helium, you can get down to fluorine. And this is how we used it. We had my samples that we dried out, took a mortar and pestle to them to get them ground up, and then we tamped them down in the sample cup to take the reading. All of that because moisture levels and air gaps in the samples will contribute to inaccurate readings. We just used the built-in calibration that came from the manufacturer for soils, which is fairly accurate based on everything that we saw here. Had we been looking for higher levels of metals in the environment, had we been looking at that 5,000 part per million range or that 2,000 part per million range, it would not have been as accurate. But for what we actually saw, which maxed out at about 400 parts per million, it was perfect. So why do I think it was perfect? That top left graph there is my initial round of dilution series where I was basing my masses spiked in either on how much copper is present in my compounds or how much copper the labeling said was present in my paints. As you can see, one axis is my target concentration, the other axis is what the XRF reported. So if I was perfect, I would have a slope of 1 on this thing. And as you can see, I only have up to 1,000 right here, and we're already starting to get off. The XRF reported values are low. If I zoom out, I went up to a 5,000. You can see it gets even worse as we get higher and higher in concentration. I kind of tried to model this. I gave it a slope of 1 and an intercept of 1.5 based on my XRF readings for the Y River. And then I asked it to generate, I did the math to generate R squared values, and I ended up with what you see there. We have a 0.77 for copper antifouling, 0.93 for copper 1, and 0.71 for copper 2. So 0.7 is kind of where you would kick in a really tight, significant relationship. So we can say these are close, they're not perfect, but they're pretty much in line. I also asked Excel to generate me trend lines, and it had slopes that were approaching 1, if not exactly at 1 for each of these data series. In the lower right-hand corner, that is my XRF dilution series, my XRF-based abrasive media dilution series. To make that, we scanned the abrasive media first, and then we made a little prototype dilution at like 1 part of abrasive media, 25 parts soil, scan that, and then we use that to decide how much to spike in for the production spike, which ended up being 800 to 200 grams. When we did that, we were a little high, so we adjusted again. We added another 200 grams of clean sediment on top of it and got down to, as you can see there, at about 1,100. And then we diluted from there, and the correct ratio is clean sediment. As you can see from my numbers, we're very tight on 1 there, but that is because we were targeting the XRF. So because one of my axes is the XRF, of course, it matches pretty close. And now onto the toxicity testing. We used EPA toxicity test methods that we had modified after some of the literature we found for lower sediment levels and water and number of organisms. So we used about half as many as the standard one, 10 organisms per test chamber, 225 milliliters of filtered seawater, and 75 grams of sediment sieved down to 300 microns in each chamber. We added overlying water on the first day and changed it out the next morning. And we had a total of 60 test chambers available to us. For our final test, we needed some extra. We managed to finagle in an extra 10 to 12. Our test organisms were amphipods called Leptochirus plumilosus. You see them down there in the lower left. And our endpoint for the test was survival. We collected growth data, but the test was sufficiently short. It's a 10-day acute test. We did not get any really significant info out of that. I did mention that I thought I'd lost some copper. So this is what I'm talking about there. For each of my dilution series, I retained one of my high treatments and did not collect survival data on it. And I scanned it after the test with the XRF to see how much copper was present. I also scanned my production spike that I put in there to see how much I had before. And as you can see, copper 2 sulfate and used abrasive, I didn't see any changes. But for cuprous oxide, my new copper antifouling paint and my used copper antifouling paint, I did see decreases in my amount of copper in my sediment. We don't know for sure why that is. We think it could be a loss to the overlying water. That doesn't necessarily explain it entirely though, because our copper sulfate is water soluble, if you'll recall. So we would have expected to lose it to the overlying water in that one, and we did not. So we have to do a little bit more thinking on that. I did try to use the XRF on my overlying water from before the test and after the test, from that day 0 water to the day 10 water, to see if that indicated any loss of water. But I did not trust that any of the calibrations built into the instrument, which are heavy metal or precious metals, soils, and plants, would read water accurately. So we just used it in a uncalibrated mode. So it gives you those overall counts. It doesn't give you parts per million or percentages or anything like that. And we didn't see anything really conclusive for our copper. Those are all more or less the same. There's some differences, there's some growth, there's some increase, not enough to say anything conclusive, and I didn't see any loss of copper in my abrasive tests in the first place. So I didn't expect to see more copper. I did see a little bit more change. I also did it for zinc. But again, nothing that really showed that we had lost copper to the end of the test. For instance, one of my samples from the 1000 replicate A, we gained zinc somehow. So more questions to figure out on that. And just a quick photo of what my 2 high replicates of the original copper compound looked like. Copper sulfate is there on the left with some blue precipitate. And copper 1 on the right there does not appear to have any precipitate. So we're still trying to figure out why we have some variation in our amounts from beginning to end. So our toxicity test results compared to our XRF results. I took our series that I'd scanned with the XRF, and instead of using the nominal target concentrations, I plotted them with what the XRF reported. So for copper 1, we ended up with this curve. Copper 2, we ended up with this curve. Copper 1 has higher survival at very similar concentrations. We think that is because of the solubility difference. When we throw in copper anti-fouling paint, it's very similar to copper 1, which checks out. It is copper 1 based anti-fouling paint. Our used paint had a little bit more survival. And we don't have an explanation for that, except possibly that because it had been in use for 3 to 5 years, it had lost some of its effectiveness. But it's still pretty close at a lot of these points. And in fact, at 500, it was totally fatal, which you can't say for some of these other ones. Finally, we did our abrasive media. As you can see, the 2 that I want to call out in the top left corner there, you can see them, they overlap each other a ton. There's one that is black and one that is yellow right there. Those are our control and our clean abrasive spike for this series. The clean abrasive is just abrasive blast media that we purchased at the store, hadn't been used for anything, at a slightly finer coarseness than our production one, thinking that, hey, it'll be a control, but also it'll be finer, maybe it'll be more bioavailable. We can say with reasonable degree of confidence that that is inert, like control, it does not cause any harm. So all the toxicity later on is due to my paint that's been contaminated into the sediment. This, I just zoomed in a little. Our abrasive series didn't go over a target of 1,000. So this just zoomed a little tighter so you can see how closely they align with each other as they increase in copper concentration. Not perfect, but close. This is an overview of that same data. In particular, I want to call attention to the LC50s. Cuprous oxide, copper 1, has a very high LC50, and we think it's because we had a loss of copper and the organisms just didn't see as much. The others are all fairly close, which reassures us that the copper is a useful predictive tool. So far as our field collected sediments go, I tried to have 2 controls, one in Maryland on the eastern shore at the Wye River in an agricultural area, which I did not expect to have much, if any, copper. And then I tried to find one in Ohio that was reasonably close to Cleveland, so I could go out and get samples while I was also in Cleveland. I found a residential area, but it is not a agricultural area. So it's the town of Lakewood. You can see right here, that is a sewage outfall from the Lakewood wastewater treatment plant, which is right here in a bend in the river. There's another outfall on the other side off the map. There is a ton of recreational boating traffic. The site that I sampled, which is there, and there, was at the Emerald Necklace Marina. It's owned by Cleveland Metro Parks. I'd hoped it would be a good control because they don't allow painting, but we saw 40 parts per million of copper, which isn't extremely high, but it is It's higher than the 1.5 average that we saw on the Wye River. Most of the sample shots I took of our control sediment were below the limit of detection, which ranged between 3 and 8 parts per million. And we had, I believe, one shot at 9, and out of all my shots, that averaged out to a 1.5. The Elizabeth River in Virginia, Norfolk, is a site that we selected for a certain amount of salinity and a large amount of shipyard activity. This one, I could get out and come back and do a dissertation on the history of these shipyards, because it's really cool. 1767, the first one was built down here. Norfolk Naval Shipyard was built by the British. It was called Gosport Shipyard. Colonus, right there, was founded in 1867. And Lyon, right there, it's on both sides of the river. I believe this is the older part. Was founded in 1928, but they bought property from a company called G.T. Taylor Marine Railway, and a marine railway is just a dry dock. There have been yards here forever. So, in theory, you could see a lot of traces of anti-fouling paint over the years. There are a total of 3 shipyards here. NASCO down at the end, owned by General Dynamics, does a lot of Navy work. Colonus West and Colonus right here on this peninsula do a lot of commercial and Coast Guard work. And Lyon right here, north and south of the river, does Coast Guard and commercial work. They all have multiple yards, travel lifts, cranes, floating docks, all kinds. And there's also another small facility here that has a travel lift for lifting small boats, but does not have any boats on the pier, and is not, as far as I can tell, a shipyard. Down here, very, 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 very residential. We were hoping to see a gradient, less copper to more copper. That's not exactly what we saw. We have 105 parts per million right there in that very residential area. And then our next 2 highest are down here, 150 underneath that 264 bridge, and 196 there in the slip at the Norfolk Tides baseball stadium. Those 2 high sites are downriver. They are in little embayments, kind of where some depositional sediments could have settled. But we don't have that systematic grid that would let us say confidently, yes, this is from the shipyard. I also, for my graph here, I didn't just run copper. The XRF gives you every element. So I did populate zinc and lead on here as well, because they are frequent co-contaminants with the copper. And you can see that zinc is frequently higher than copper, not high enough to be toxic, because its toxic level is a lot higher than copper's is, but elevated. And lead is also fairly elevated in a lot of these sites. Again, can't conclusively say that that is shipyard related, because this is a very industrialized river, but it has had a lot going on there over the years, but it does indicate that this is a useful tool for these assessments. Curtis Creek in Baltimore, Maryland, you probably recognize 695 headed towards where the Key Bridge used to be over there, is another site that we chose because it was a very polluted industrial river, and it was the opposite end of the spectrum on shipyard activity. There is one shipyard here, Coast Guard Yard, right there. There are some other sites of interest though. U.S. Army Depot Curtis Bay is an old ordnance depot, so it's also another possible source of contamination, but it is not, as far as I can tell, a brownfields or a Superfund site. Tan Yard Cove down here by Site 7. On the shore, on the southern side, there's a CSX property that has been contaminated over the years by just random people dumping stuff. So it's another brownfield site. Neither of them is an active contamination concern. And Coast Guard Yard is a Superfund site for a variety of reasons, but including sediments from the hull cleaning and painting work. It is construction complete as of 2013, so they've done all the remediation they intend to. Part of that project included dredging a bunch of sediment, 6,000 tons, through Arundel Cove here and down along the pier face right there. End result of that long spiel is that there was less copper than might have been interesting. As you can see, Arundel Cove, there are old marine railways right there, and there have always been ships moored there, and there's very little water movement, but there's very little copper through there. And there's a lot of very sandy sediments, likely because when they dredged it, they dropped sand, and anything that is left there is kind of capped off by that. Our high points were 100 parts per million out there on the way to the harbor, and there's 20 parts per million right next to it, so it's not really conclusive, but we were trying to target another one of those little depositional areas where that little bay could have caught stuff. Our high point is 153 parts per million right there, which is directly off of that yellow dot. That yellow dot is the location of the current ship lifts dry dock. It is also where they previously had 2 marine railways and where for many years they docked a very large floating dry dock. The sediment that we pulled up was very dark and anoxic and full of chunks of leaves and twigs, so i.e., I'm pretty sure that's a lot of organic content. The fact that it is higher copper makes sense for that reason. And similarly, copper and zinc, or zinc and lead are elevated along with my copper. The Cuyahoga was my final site, and I was going for freshwater, limited number of shipyards, and highly contaminated. I'm sure you've all heard about the many, many times the Cuyahoga caught on fire. It's better now, we swear. Tons of sites of interest here. So, right there is a water treatment plant for drinking water. Right there is a brownfield site that is owned by the water treatment plant. It's not a contamination risk, but it is a brownfield site. It used to be Superfund. Right there is Channel Park Marina. Along here is Great Lakes Shipyard. There are 2 sewage discharges there and there. And just for added fun, right there is a salt mine, and that is a sewage treatment plant right there. And I only just recently discovered this, but this, which I thought was a channel, which I didn't manage to get a sample of, is an old graving dock. Between 1860 and 1870, there were shipyards all up and down this old channel. In 1827, they altered the flow of the river. They had it go out here for the shipping channel, and they closed it off down here. And after that, it industrialized a ton, and that's when all the yards started to get built in the decades after that. So again, there could be, that's more than a century of worth of contamination from shipyard activity. Photo of the graving dock, which I found and thought was super cool. Unfortunately, fortunately I should say, we do have a copper concentration here at that western edge of the channel. The unfortunate part of it is that it is much closer to the marina for recreational boats and to those old graving docks. There used to be 2. One is filled in and it's now a storage barn for the marina. It is not super close to the shipyard. I had hoped that I would find out, oh, the prevailing winds are out of the east. So it's just blown here from the shipyard. The prevailing winds are from the west. So that doesn't make sense. And the flow of water is out to the lake. There is no outflow this way. So I don't have a good rationale for why all the contaminants settle there. But that is where our high copper is. That is also where decades of contamination are from PCBs, and PAHs, and supposedly cadmium and mercury and lead, which I didn't really see a ton of, elevated, but not crazily. So this one was interesting, and we were very helpful for our toxicity results, which are up next. XRF results are up next. Compare distance to the dock to copper content. Docks being defined as I picked the point in each shipyard that was a dry dock. Many of the shipyards had more than one dry dock, so it's not conclusive. Many of the shipyards have travel lifts, so the boats get picked up and driven somewhere else, so it could be anywhere along the shore. We didn't have a conclusive, heck yeah, every high concentration is close to a dock, but all of our low concentrations are, all of our further away samples are lower. So with a more systematic sampling methodology, we might find out that yes, there is a definite relationship there. I also did indicate that some of these are upriver and some of these are downriver. Triangular dots indicate downriver from the site, so maybe they could have some more settling waste from the dock, but I don't have any conclusive statistics for that. Finally, to our field sediments. This is our abrasive series, which you've already seen. I spiked it. I know how much copper is in it. I'm providing it as a reference for what we would expect to see based on copper levels. This is Curtis Creek. There's not enough copper to do anything. Totally unsurprising. Sweet. This is the Cuyahoga. I was very excited. We had a 200 and we had a 378, both of which I expected to see toxic effects. That's our 200. We had some substantial toxicity. It is roughly in line with my abrasive media sample at a similar concentration. And then my 378. Survival everywhere. There's a couple of different possibilities for why that could be. I'll get into those next. And then the Elizabeth River, which might as well have been a control. It didn't do anything. Lots of survival everywhere, which was surprising, but there's different branches. The other branch might have been worse. There are a lot of confounding sources for copper. Typical levels, because I've talked about how much I have and not how much you'd expect to see. USGS has a median level in sediment of 30 parts per million. NOAA did a contaminated sediment, coastal sediment survey, which indicated that about 2% of coastal rivers had 210 parts per million or more, and about 25% had 42 to 210 parts per million copper, and everything else was below that. So we're in that top 27% with a significant number of our samples. Some of the other sources for copper are those residential uses of copper sulfide or copper sulfate as a root killer and as a fungicide, or agricultural sources, including as biocide and a feed additive, combined sewer outflows, which can take results from all of that, and also from copper pipes. They can strip some stuff out of there. And finally, the marinas. There in the middle, you see a photo of our marina Channel Park directly across from our shipyard. They're very close together, so that's difficult to disentangle those two. And there are quite a few confounding influences on toxicity. A lot of work has gone into creating models for how the different characteristics of sediments and water will affect the toxicity of total metal concentrations. Some of these include that toxicity will decrease with higher organic carbon contents. It will increase with higher temperature and pH. As salinity increases, it will first decrease and then increase again. And then there are other factors that'll tie into it, like your grain size will affect how much copper, how much metal in general, and how much organic content there is, and the exact species of metal and the charge and all that will also affect it. There are a number of different models that they've tried to use to deconflict this. BLM, the biotic ligand model, is mostly used for water quality rather than sediments. It includes a lot of these factors, including temperature, pH, dissolved organic carbon, cations and anions that are predominant, alkalinity and sulfides. The WER, the water effect ratio, is just a way of basically adjusting from the lab to the field. You get an LC50 for both, and then you divide them, and that gives you a ratio when you're going out to evaluate sediments from there at that specific site. And AVS-SEM, the acid volatile sulfide, simultaneously extracted metals, is one that's commonly used in the sediments. It compares the ratio of sulfide that can be extracted by acid to metals that can be extracted at the same time to kind of give a benchmark for how much those metals will bond to carbon content in the soils instead of being available for organisms to encounter. And then there's some miscellaneous other models that can be used as basis for understanding how this works. Overall, in conclusion, I'm at 40 minutes. We're probably about out of time for the room. I was able to say that, yes, we do have elevated copper levels in these rivers. I can't conclusively say that it was because of the shipyards, but I can say that it's suggestive and that this method works for getting initial numbers for sediments in these rivers. You could pull some sediment and dry it overnight and have a result the next morning. Or have an inaccurate result the day of if you want to stick your expensive instrument in some dirty water. And I did generally get a result that says that the copper induced toxicity in my field sediments matches my spiked sediments in the lab, with the exception of my 378 that didn't kill anything, likely because of that organic carbon content. And that's it. So there. I believe we have 3 minutes for questions, which is what I expected, so I did well.
We have plenty of time for questions.
We have plenty of time for questions.
Love this work. So do, you know, the stuff that's already in the sediments that's in the sediments, right? And it's nice to see that, that the Coast Guard station remediated around it. And that's probably why you got some lower levels there, right?
Yep, exactly.
Fine. Do they, you know, there's scraping and repainting, but do they haul their ships out to just water blast their, the bottoms to get the biofouling off and put them back in?
So that varies based on a couple of factors. So I am currently, like Dr. Younger said, I'm going to small boat product line. We work on the boats that are under 65 feet. Those get hauled out every year. They will get their hulls cleaned in, and they will go back in the water. My previous job was icebreaker, buoy tender, and construction tender product line. We worked on ships like that, actually, 225-foot seagoing buoy tender. It's bigger, it is more expensive to dock. That's going to get docked every 3 years. Any hull cleaning in between would be done by divers. Or, as an aside, the Great Lakes doesn't use very much anti-fouling paint. There is ice. Icebreakers do not use anti-fouling paint because when they run through ice, everything gets stripped off. Free hull cleaning.
You had a figure there, percent survival of what? what kind of microorganisms that you were referring to?
So we were using Leptochirus plumilosus. They are small estuarine saltwater amphipods.
There was another one that you had that was really very decaying function quickly. Anyway, between this and that, did you all identify a threshold, basically copper concentration at which basically there is no creatures living?
Yeah, so pretty much by the time we got to 2,000 parts per million copper, everything was dead. And several 1,000 was that threshold.
We had another figure that was very drastic to the decaying function.
Yeah, it was probably.
Sorry,
Yeah, no, you're good.
This one.
Yep,
yeah.
this one.
That's what my eye, the one that prior to this, yeah.
So this one might be, this one's actually zoomed in. It's perfect. This is on the same scale. It maxes out at 1,600. So it's roughly similar to the one at the end there. I don't think it is all that different. I think it's just formatted a little differently. That blue series is also on the last one as my kind of reference guideline. The most rapid drop in survival was probably in our used anti-fouling paint because they were pretty much all dead at just over 400. And we think, or I think that is because the used paint was really powdery and dissolved and easy to access for the organisms.
As you know, that can determine, in other words, if we are able to define threshold value, that can determine in practice, right, what kind of paint we're going to use, what concentrations of copper and so forth, that is environmentally safe, quote unquote.
Yeah.
That's why I was referring to this.
So we did generate no effect and lowest observable effect concentrations here. Or tried to. We didn't get actual no effect concentrations for most of these. We just got below the low effect. And it's generally in that 100 to 300 range, at least for these sediments.
Thank you. This is great work.
Can you go back to the graph you just had a second ago? Okay, so the one with the 1,600 is fine. So just as a little bit of a softball, I'm going to throw you here. All of these were made up in the lab using Y sediment. So they all had the same matrix with some coppery stuff added to it.
Yeah, so this.
How's that differ from the other ones that you were showing?
So this removes those interferences. That whole last slide where it's the difference in organic carbon, the difference in grain size, the difference in pH, difference in salinity, they're all more or less the same. The others, it's not the same. One of those sediments was even a freshwater sediment that we'd added saltwater to over the top of. There's a lot of interferences. This one purely says all other things being considered equal, copper is what determines the toxicity. Did I actually answer the softball or?
Pretty much, yeah. I mean, the notion of a threshold, this looks great. At the end of the day, you can look at that and say, okay, 50% survival, it's got to be under 200. And that agrees really well with pretty much all of those other regulatory things. The US refuses to put a sediment one out. So some states have done it, but Canada's put one out, Australia's put one out, and they're all 200 and less, right?
Yeah.
As a safe number.
But they all have a water quality discharge threshold that you're not allowed to.
Yes, everybody has a water quality.
But for sediment,
I mean, once it's in the sediment, unless it's like a matter of determining we're gonna have to dredge this out and remediate and cover it with sand. So there's that.
right.
And trying to keep it from getting in the first place, but this is legacy stuff.
Yeah.
Me.
Yes, sorry.
Yeah, so that kind of introduces my question, which is maybe a step after this, once you detect this is a good method for detecting, like what is the remediation that they would use in the sediments?
So capping is the cheapest. If you just put inert sediments over the top of it and then don't disturb it, you're good. The other one is just removal. You dredge up all your sediments that you can and you dispose of them in the most environmentally friendly way you can, which the Coast Guard yard, they did some on-site treatment of theirs, and then there is a regular old landfill across the street. So they did on-site treatment and then trucks it over to the landfill. In Cleveland, they're actively working on remediating that old channel there. They're currently debating whether that graving dock at that end is going to get included or not. They're going to dump it in a structure that they built in the harbor. It's got basically 4 walls and water on 3 sides, and they're going to do the land reclamation type thing, and they're going to have the toxic sediments contained in that, and it's just going to sit.
And one little other half of that, do you have any sense as to how deep the
Short answer is yes, there is a depth gradient that's associated with this. I just took very shallow surface samples, so I don't have those numbers. But a lot of them, as you go deeper, you get more of all kinds of contaminants. Copper included though, because they've been using these paints for decades. And even before that, when they were wooden ships, they were nailing copper bits to them to keep them from getting organisms growing on them. I think you had a question?
So just building on that a little bit, in terms of, going back to the paints, right? So you bought these at Sherman-Williams, or donated at Sherman-Williams, they were given the paints. With what you know about, the spilling or offsets, would you change? So if I am building something, a ballast, and I'm painting it, would you change what the regulations are or the environmental impact assessment of using these paints based on what you're finding? Is there a change in regulation or EI impact needed? Is there a larger impact assessment than what's being reported?
So that is one of those points that you are going to have to make trade-offs. Because, like I said at the very beginning, these save a ton in CO2 emissions. So is an additional impact to marine life worth cutting down those CO2 emissions? Is it worth making shipping more affordable? Hard to say. It is very likely that it is not worth it to have the marinas are huge spikes. I didn't get into it, but the marinas are huge sources of this because every Joe Schmo is out there. They pay the marina a minimal amount to throw the boat up on the pier, and then they go out there with their can of paint. They just slop it on there. We don't need to be doing that. If you can afford to have a boat, no offense, you can afford to dock it and clean it. You can afford to pay for a diver. You don't need the anti-fouling paint. So yes, it depends on the condition, but yeah, there should probably be some changes there. And some places have banned it for wreck boats.
Yeah, so Andrew, if you can hear us, you can go ahead and ask the question, and maybe this will be our last question.
Okay, go ahead. Yeah, great. So my experience with firefighting.
Yeah.
Can you hear me?
So if you try to turn the volume.
I can hear you guys. Can you hear me? So you can't hear me, I take it, right?
Yeah,
I
we
can
can hear you.
Okay, you can hear me now? Okay, good. So my question is based off of my experience with firefighting foams, where one of the ways that the Department of Defense has been able to sort of, slowly steer products towards lower hazards has been through, the performance specifications. Are you aware of any sort of discussion about the performance specifications for anti-fouling paint, either focusing on specific ingredients or the whole product toxicity, which, generally is an efficient way to sort of inform these things, especially with the, new impetus to build a lot of ships. I'd be curious if there's discussion about modifying the performance specifications to actually specifically address hazards.
So yes and no. The way ours are managed, our contract specifications are managed by Surface Forces Logistics Center. They're altered at a very low level, so there's a middle manager who could change that. We don't have anything that we've changed based on our paints, or our specs for our paints, or what's approved there, but we do have a variety of controls that we've implemented requiring increased levels of containment. So generally speaking, the project that we are on is supposed to have something very similar to what a project that we're funding, that we're paying for, is supposed to have something very similar to what the Coast Guard Yard has, what they require in Washington State, regardless of the local or state regulations, because it is a contract specification. That is an engineering control. That is not a policy product development control, and it sometimes varies in implementation and enforcement.
Good. Yeah, it does. Yeah, that's great. We did this with firefighting foams. They did both things, change the product and get into the engineering control. So yeah, cool. Thank you.
It probably wouldn't be a bad idea. They are every company out there. I haven't heard anything from the industry side of people who apply the paints, but every company that makes paints is researching some kind of novel variation on the theme, whether it's enzyme based or whether it's new non-chemically active coatings, or whether it's pharmaceuticals that they're adding to the paints. Just anything they can do to reduce the copper loads so that they can reduce the likelihood that that's going to get outright banned.
Yeah,
They
Yeah.
want alternatives.
yeah, the performance specifications are a good way to really drive that, but you gotta get with NAVC to make that happen. It's a
Yeah.
slow
Or-
game too.
Yeah, most of our stuff for that is NAVC. We just follow them. We don't.
Yeah,
We
cool.
don't do the original.
Yeah, thank you.
All right, all, so, one more round of applause, and,